Ostwald dilution law and relational dissociation constant. So Ostwald dilution law says when you take a weak acid and the solution is diluted, so what happens? You can neglect the concentration of water. So let's take an example of your monoprotic weak acid HA, and it dissociates into H positive and A negative. For the simplification, we have ignored the water here, and that's why instead of writing H3O positive, I have written here H positive. So if you take the initial concentration, let's say this is the concentration of HA, C moles per decimeter cube. So at initially what you have, the concentration of H positive and A negative are 0, since there is no dissociation at the initial stage. And if alpha is the degree of dissociation of HA, then at equilibrium position, the change in concentration of HA is from C to C into 1 minus alpha. So alpha, so at equilibrium, your concentration changes from C to C into 1 minus alpha, and the H positive and A negative formed are C alphas respectively. Now at equilibrium, if you have to write down the value of acid dissociation constant, it will become C alpha into C alpha divided by C into 1 minus alpha. Alright, this concentration has been put here. The formula would have been HA is equal to H positive, A negative, and your HA. So what I have done here is I have put the values of these here. Now your dissociation degree of dissociation is very small. It's a weak acid, so the alpha is very small and it can be neglected as compared to 1. So we can write 1 minus alpha equal to 1. Yeah, I have written it here. So we can write 1 minus alpha equal to 1. So our Ka becomes, this becomes C alpha into C alpha divided by C. Alright, so our Ka becomes C alpha square. And if you have to write alpha in terms of your equilibrium constant and concentration, the formula becomes this. Alright, now here we had the concentration of H positive as C alpha. So putting the value of alpha from here to there, what you will get, under root of your acid dissociation constant into initial concentration of your acid. This will give you the H positive concentration of your proton. From this you can also calculate pH. pH is nothing but minus log of H positive. Alright. Now if you consider a weak base, so we have taken the same general reaction, B plus H2O to give Hb positive plus OH negative. So here OH negative will be, it will have similar kind of derivation as the acid, and the relation will be under root Kb into C, and similarly alpha will be under root Kb by C. The next thing that we have to study is ionic product of water. What happens when you have pure water? Very little self ionization, or you can say auto ionization of water takes place. If water have some dissolved ions in it, then there is more ionization of water. But if your water is pure, then the ionization of water is to a very smaller extent. So let's see, if you have water in liquid state, then on ionization, very small amount of H positive and OH negative will be there. All of you must have studied this, that if water have some substance dissolved in it, some ionic substance, that time only it can transfer or transport the electricity. But if you have pure water, it will not conduct the electricity. The reason is only this, that in the pure form, the dissociation or the ionization of water molecule is very less. So let's come back to our equilibrium constant. Equilibrium constant is equal to concentration of your products. So that is H positive and OH negative divided by water. And since this we have already discussed, degree of dissociation is very small, so the concentration of water can be considered as constant. So here in this equation, our concentration of water is constant. Now what we can do, we can take this constant to the left hand side, where on multiplication to our equilibrium constant, we got a new Kw. This Kw is nothing but ionic product of water. Alright, and this way you can calculate the value of your Kw. This can be found out using the values of H positive and OH negative. Once they multiply with each other, you get Kw equal to 1.0 into 10 raised to power minus 14 mole square decimeter raised to minus 6. Alright. Next thing is measurement of acidity and basicity. Alright. So you must be doing the pH test using a litmus paper or pH meter. So that instrument or that pH paper is used to measure the acidity or basicity of any solution. So pH is nothing but negative logarithm of concentration of your H positive. This. So what does this tells us? This tells us whether our solution is acidic or basic. And what it does, it means is whichever the ion among H positive and OH negative, the one which dominates results in the acidity and basicity. For example, if you have both the H positive and OH negative in same concentration, then the pH will be 7, and this means that your solution is neutral. Alright. Second thing is, when H positive concentration is higher than that of OH negative, that means the solution have more of H positive present. So this suggests that your solution is acidic. Or in another word, you can say it will have pH less than 7. Similarly, when you have more of OH negative, that means it is basic, having pH more than 7. So it's very simple. If your pH is 7, that means neutral. If you have a pH less than 7, that means it is an acidic solution. If the pH is more than 7, that means it's a basic solution. And the way pH is defined, in a similar way, pOH is defined. pOH is negative logarithm of hydroxide ion concentration. Alright. So this can be written as in the terms of pOH, but majorly when we are describing the acidity and basicity of any solution, we mainly use this equation. We mainly measure the pH of that particular solution, not the pOH. Now, the pH and pOH is equal to 40. These two terms collectively remains constant. It never exceeds or never decreases from the 40. It is always constant and it is 40. Alright.